Okay, maybe it's 4 on my clock, so we can start already. So welcome everyone to session 4 of APPROX. We'll have 4 talks, 10 minutes each, and people should feel free to ask questions, maybe either through chat or you can also unmute yourself and ask question if you like. So the first talk will be by Shamantak Das on approximation for capacitated min-max tree cover. So Shamantak.
Yeah, thanks, Nikhil, and thanks to everyone for attending. Yeah, so this is a joint work with Lavina, who used to be my undergrad student, and Nikhil, who is still a PhD student at IIT Delhi, and he would be graduating soon. Okay, so the work which we did here is related to a variant of a popular problem in combinatorial optimization and operations research, which is popularly known as vehicle routing. So I'm going to show you one version of vehicle routing. There are several other variants. So suppose I have a bunch of client locations, which I show here as the P's, and I have a bunch of vehicles. I have a fixed number of vehicles, and they are stationed at these depots, which are marked with V. And the idea would be to find a tour of these vehicles so that I can cover all the clients. Yeah, very simple setting, very standard setting of vehicle routing. And so for example, this is one possible vehicle routing cover. So right now, which one do I choose among several such possible coverings? Well, I want to choose the one that minimizes the maximum distance that is traveled by any vehicle. Yeah, so this is also popularly known as the make span of the solution in our literature. So that's the kind of the objective that I'm looking for this talk. Okay, what I'm going to talk about is not exactly the vehicle routing problem, but a close ally of that problem, which we call the mean max tree cover problem. Yeah, so the setting is very similar. I have just removed the depots or the routes, if you may want to look at it, so that it's simpler to explain. So suppose I have a bunch of points, and I want to find a union of trees, a union of a fixed number of trees, so that this union covers all the possible points. Okay. There is one subtlety to note here. I am not looking for a partition of my graph. So the trees don't form a partition of the edges. What is only required is that the union of these trees should cover all the vertices. Yeah, this is very important for our work. Okay, so now this has been studied for quite some time now, but what we study here is a capacitated version. Okay, so think of every vehicle sort of having like a capacity, so they cannot visit as many clients they want. So I'm like restricted by a parameter lambda, which tells me how many points can be covered by a vehicle, or in case of the mean max tree cover problem, how many vertices can be covered by a single tree in my solution. Okay, so that's my input. So there are now, just to summarize, there are 3 parameters. Of course, I have the graph with edge weights, and I have a parameter k, which bounds the number of trees that I can use. And I also have a bound lambda, which tells me how many points each tree can cover at the most. Okay, and again, I want to minimize the maximum length of any tree. So I hope the problem statement is clear to everyone. So let's take a look at what is known about these sort of problems. So for the uncapacitated version, both for the rooted and unrooted cases, there are very small constant factors known, although these are not tight. So there's a 4 for the rooted version, there's a 3 for the unrooted version, while the only lower bound that we know is a 1.5. So there, of course, is a gap. Okay. However, surprisingly, the capacitated version has not attracted much attention so far. So the only known result, to the best of our knowledge, is this old result by Gutmann, Beck, and others. And that also for a very special case where they assume that the total number of vertices in the graph is like k times lambda. So each tree will have exactly lambda number of vertices. And there they give a 2k minus 1 approximation. Okay. So we kind of try to close this huge gap in this work. And what we prove is that for the capacitated version, both for unrooted and rooted cases, we can have a constant factor approximation. Okay, so that's the main result of this work. So let me give a very, kind of a bird's eye view of what the main techniques are. So here is the first very simple observation, which is that if I look at any optimal solution to my problem, then this optimal solution is nothing but a union of what I call the lambda MSTs. So these are known as KMSTs in literature, but I avoid K because K here means something else. So lambda MST simply means a spanning a graph, a subgraph of my graph, a tree, which is a subtree of my graph, which spans exactly lambda number of vertices. Okay, so for simplicity, just think about the simple case where every tree here will have exactly lambda vertices. Yeah, so opt is nothing but a union of k lambda MSTs. So a natural idea would be to start finding these good lambda MSTs. Okay, now of course finding a lambda MST is NP hard, but we can use a known approximation algorithm for this, which gives a 2 approximation. So let's start doing that in a greedy fashion. Now here is a problem that we land up on. So suppose the optimal solution looks like the figure on the left, on the extreme left. So these are the 4 trees that are created by opt. Whereas my greedy choice might end up picking some trees which have low cost. But the trouble is that once you have picked these 3 trees, you are kind of stuck now because there are still 4 vertices which are yet to be covered, but you don't know how to find a cheap lambda MST that can connect these up. Okay, so now what do we do? So that brings us to our next observation, which is the following: that although these guys are left out, the reason that they have been left out is the following: that my solution have sort of separated the vertices that belong to a single tree in the optimal solution, which on the good side, it means that every vertex that I have left out has to be quite close to one of the trees that I have been able to create in my greedy procedure. Okay, and this kind of allows us to set up now a bipartite matching formulation where I put an edge between a vertex that has been left out to a tree that I have formed only if they are fairly close to each other. Yeah, so I can guess optimal and I can create this bipartite graph. And now I attempt to find a perfect matching in this graph. Now you might think that, okay, what's the guarantee that there will be a perfect matching in this graph? And well, the reason I want a perfect matching is because a perfect matching will mean that already the trees on the right hand side are of low cost. And then I will incur another opt cost in order to connect this left out guy to this tree. So in all, I will be a constant factor away. But what's the guarantee that I will have a perfect matching? I mean, it can very well be the case that several of these bad guys are close to a single good guy on the right hand side. And that can indeed be the case, which in fact means that there is a Hall set in my graph. But then we show that there is a way you can handle this by sort of iteratively removing the Hall sets. And for that, we use the uncapacitated K-tree cover algorithm. So there's a 3 approximation known. And of course, we lose constants in this process, but that's how it is. So that's the overall sort of the idea of this algorithm. So I really don't have time to go into these details. So here is the summary of our main result. So we have a constant factor approximation for the capacitated mean max tree cover, both for unrooted and rooted version. And let me end with a couple of open questions. So the first would be to improve the constant, which is quite large right now. It's close to 200. And an LP with a constant integrality gap might be interesting direction. And the other would be to prove a PTAS for special cases like tree metric or Euclidean metric. So there is a PTAS known for the uncapacitated version on the tree. It's quite a recent result. So yeah, one might be interested to see if we can do this in the capacitated case. So yeah, thank you for listening.
Thank you. We have time for a couple of questions people have. So maybe I'll ask a quick question. So your
Yes.
algorithm is completely combinatorial, like you don't use
That's
any
right.
LPs.
That's right. That's
even
right.
in the
That's right.
KMST or anywhere.
No, KMST is primal dual, so like we don't need the LP as such. But yeah, I mean we don't need to solve the LP, but yes, we use LP in that sense. Yeah.
Okay. Are there?
If you allow bipartite solutions, if you allow someone to go above the capacity by a little bit, does it?
Yeah.
Here, can you get like a small constant?
Right. So, so the point is, I will sort of, so I did not describe this step. So this step we can avoid if we want a bicriteria. So the constant that we, so at least in our technique so far, the constant, we lose sort of a 12 factor in this step, which I really did not have time to go through. So that will be avoided, at least in the current form. So we can just end it here, sort of. Yeah.
Okay, thank you. So we will move to
Thanks,
the next talk. And thanks,
Yeah.
Amit, again. So the next talk will be by Qian Xiang on polylogarithmic approximation for k-connected directed Steiner tree on quasi-bipartite graphs. So Qian, please go ahead. We don't hear you, Qian. Are you? I think you're muted. So can you unmute, or maybe Andreas can unmute?
I'm trying to unmute him, but it doesn't work for some reason.
Can you hear me?
Ah.
Now we
Yes,
can hear you.
Yeah.
Oh, okay, sure. That's good.
Okay. So maybe yeah, let's start. We didn't hear anything, so start again.
Wait a minute. Okay. Hello, everyone. I'm Jin Xiang, and today I'm going to talk about an approximate algorithm for k-connected directed Steiner tree on quasi-bipartite graph. And this work is joined by Bang Di, Yu Hao, and Hao Ting. Okay. So first, we define the k-connected directed Steiner tree problems. So given an non-negative edge cost directed graph with a root vertex, a set of terminals, and the others are called Steiner points. We want to find a mean cost subgraph such that there are kh disjoint paths from the root to each terminal. Okay, so for example, if we use black vertex to denote the terminal and the square vertex to denote the Steiner point, the red edge subgraph is a feasible solution of two connected directed Steiner tree. Okay. So next, because our work is work on quasi-bipartite graph, so what is quasi-bipartite graph? And quasi-bipartite graph is a graph with known edge cross between two Steiner points. So for example, on the right-hand side, is a quasi-bipartite graph, and on the left-hand side is not a quasi-bipartite graph because there's edges cross the Steiner point. Okay, so there's our main result. We propose a randomized polynomial time algorithms for approximate ratio log Q log K, where K is the connectivity requirement and Q is the number of terminals. Okay. So we also provide a deterministic version of these algorithms. So compared to previous results, they only work for K is equal to 2 or need to have assumption on the structure of the optimal solutions. Our result is independent with the structures of the optimal solutions and can serve for arbitrary K, though the algorithm is restricted to the class of quasi-bipartite graph. Okay, so this is our algorithm framework, and we want to find a subgraph that has K distinct paths from the root to each terminal, and we want to minimize the cost. So our algorithm in high level is combine the connectivity augmentation framework and the hollow set decompositions. Okay, so in the outer loop is the connectivity augmentation framework. So that is, we start with an empty graph, then we add an edge to let each terminal has at least one path to the root. And then we keep repeating the process. And in each iteration, we add an additional edge disjoint path from the root to each terminal. So the connectivity requirement will keep increasing. So this process will give us a log K factor in the approximate ratios. So how do we increase the connectivity in each round? We use the hollow set decompositions. So suppose let's suppose we can have a polynomial many partition for those terminals which we need to add a new connectivity from the root. So we call those partition as a hollow set. So in each round, we can choose a set of edges whose cost is at most constant times the optimal solution of the LP relaxations of the KDST problems. And we make sure that there are at least constant fraction of hollow set will be covered in each sub round, which means in the loop. And so this guarantee that we can spend a low K times loopings to cover all the hollow sets. So this will give us a low Q ratios, where Q is the number of terminals. Okay. So we can bound the cost because the quasi-bipartite graph properties enable us to mapping the hollow set covering problem to the facility location problem. And this mapping is the key in our work. So since the facility location problem have a polynomial time algorithm with low Q approximate ratios. So to see the mapping, so first we introduce what is hollow set decompositions. So suppose that we already partition all the terminal into polynomial many hollow sets, and each set is not a subset of others, so they can only intersect at some part. So in particular, we show we can use the red edges, say on the left-hand side, for example, is E1, and some orange corresponding orange edges to add up the connectivity of the terminal in a hollow set. And we call those edges cover such hollow sets. So we call the red edges as the external edges, just cross the boundary of the hollow set, and the orange edges is the internal edges. So for example, on the left, the external edges E1 corresponding to those internal orange edges will cover the hollow set H2. Okay. So let's define the facility location problem first, and we can see the reductions. So in facility location problem, there are N clients, which is the white node, and M non-negative cost facility, which is the red node. And each facility can serve several clients with different costs, presented as the orange edges. Okay, so we can choose whether to open a facility or not, and a group of clients served by such facility. So our goal is to minimize the cost, such that each client at least served by one facility. Okay. So hollow set decompositions and quasi-bipartite graph property enable the mapping between the hollow set covering problem to the facility location problem. So first, there is the first property that there is a general that the intersection of two different hollow sets do not contain any terminals. So the intersection between two hollow sets only contain the Steiner point. And second, since it is quasi-bipartite, so we know that there do not have an edge lie in the intersection part, which means that there do not have an edge have two endpoints both lie in the intersection part, because intersection only contains Steiner point, but quasi-bipartite graph do not have any edges cross between two Steiner points. So this enables us to have a following mapping. So we can treat each hollow set as a client in the facility location problems, and each external edges as the facility. And the cost between the client and the facility is equal to the summation of all the internal edges cost corresponding to such external edges. Okay. And because the two property I just mentioned, the cost will not be like count many times, because the internal edge is disjoint. So this mapping enabled us to bound the cost of the approximate ratio. Okay. I think that is the end of my talk.
Okay, thank you. Maybe a quick question. Okay, if not, thank you, Chan, again. So maybe we can go to the next talk, Roy.
Let me
Okay, so the next talk will be by Roy Schwartz on approximating requirement cut via a configuration LP. So Roy, please go ahead.
thank you for attending. And this is joint work with Yotam Sharoni. So I'll start with the definition of the problem. So we have an undirected graph. Can you see my pointer on the screen? Or I should, okay, so we have an undirected graph. And we have groups of vertices. So in this example, we have three groups, the red one, the blue group, and the green group. And each group has a requirement, which is a non-negative integer number. And the goal is to remove edges from the graph to partition it. So we remove edges and we look at the connected components that result after we remove the edges. And the constraint is that every group is split to at least its requirement different connected components. Okay? So for example, if we remove all the dashed edges you can see now, so if we remove these edges from the graph, we have these connected components. So this vertex is a connected component, all of these are a connected component, this is a connected component, and these two are two separate connected components. And you can verify that each of the groups is split to at least its requirement parts, a different connected component. So the red one belongs to this component, and this component. The green one also to at least two, and the blue one to at least three. Okay, so this is what is called a requirement cut problem. So formally, the input is an undirected graph G. We have non-negative weights on the edges, which we call W. And there are G groups of vertices, x1, x2, and so on, which are the terminals essentially. And each group is equipped with its requirement, okay, which is a non-negative integer. And the goal is to find a subset of edges, let's call it F, such that once F is removed from the graph, so we examine this graph, once all the edges in F are removed, each xi is split to at least Ri connected components in GF, okay? And the goal is to minimize the total weight of, or the total cost of edges removed from the graph, okay? So why is this problem interesting? So this problem captures many other interesting problems, cut problems. For example, it captures multi-way cut. So in multi-way cut, we have k terminals, and the goal is to remove edges and disconnect all pairs of terminals. So in this case, if there are k terminals, we'll have one group of size k, which contains exactly the terminals, and its requirement will be k, right? So any feasible solution will have to disconnect all pairs of terminals. It also captures multi-cut. So in this case, the groups will be the pairs SI-TI we want to disconnect, and so on and on. So mean k-cut, Steiner k-cut. So this is like one problem that captures all of these, okay? So to better understand our result, I'll go briefly over the known results. And the nice thing here is that there are only a few known results, so I'll be able to review everything that is known. This problem was first introduced by Nagarajan and Rabi, and they presented an order log R approximation on trees, where this capital R is the sum of requirements when you sum over all groups, okay? And for general graphs, they gave an approximation of order log N log R, and that was improved by Gupta, Nagarajan, and Rabi, which improved the factor of on trees to log G, which is the number of groups, if you remember. And for general graphs, they resulted in order log K log G approximation. The nice thing about these two works is that their high-level approach is essentially the same. So what they do is actually write a spreading metric relaxation. So that means that the variables are distances, metric, and the points are the vertices. And the constraint is that every group is its spanning tree has a large enough length. I won't go into the exact details, but intuitively you just write a spreading metric, and then you take this metric and transform it into a tree metric, and then you round it on the tree. Okay, so here you can see that essentially the log R in the original work comes from rounding on the tree, and you use log N just by using HSTs. In this work, they show that you can, in some way, intuitively stop the construction of HSTs slightly earlier, but it's still good for this purpose, and you lose only log K and not log N. Okay.
So Roy, what was K? The maximum connectivity?
K is the size of the union of all the groups, the number of terminals. So every vertex is a terminal if it belongs to at least one group. So you take the union of all the xi's, and you take the size of the union. This is K, the number of terminals. So this corresponds exactly to the K in multi-way cut, the K in multi-cut, and so on. Okay. Yeah, so thank you. This is the meaning of K. And another thing to point is that this log G factor is essentially tight, because in the original paper, Nagarajan and Rabi actually proved that by reduction to set cover that you cannot do better even on trees. Okay. What we present a randomized polynomial time algorithm that achieves this approximation, and I'll go over this slowly, so it might look very long. So ignore this x for the moment. So we have log R as in the original work, and instead of log K, we have square root log K times log K. So up to this log factor, we shaved a factor of square root log K compared to previous work. However, we lost a factor of this capital X, which is the size of the largest group. Not the sum of the sizes, but the size of the largest one. So this result is essentially incomparable to previous results, and it is better when all the groups are small, essentially where the size of the largest group is not too large. And then we kind of shaved roughly a square root log factor from the approximation, depending on the size of X. Okay, so I'll just very briefly mention how we do this. So the first thing is that we don't use spreading metric relaxation. We write the configuration LP for this, where we have a variable for every cut, essentially, and choosing a cut means removing all edges that cross the boundary of the cut. And then we apply something that is almost a simple randomized rounding, and which is very surprising that such a simple thing works. But the heart of the analysis is the fact that we need to show that each xi is split to enough parts in this randomized rounding. And intuitively, I will just give you a flavor of what is going on here. So assume this is a group, some, I don't know, x1. And let's say in the randomized rounding, I chose 3 cuts, this, and the larger one. So by choosing these 3 cuts, and again, choosing a cut means removing all edges that cross the boundary of the cut. If this was some x, we added 3 new parts to x, like it's split to this, this, and this by choosing 3 cuts. However, if we choose more cuts, it doesn't mean necessarily that we split x to more pieces, because there are dependencies. For example, if I choose all of these, I chose 7 cuts here, I just created 3 more new parts as before. So the trick here, or the heart of the analysis, is showing that on average, randomized rounding still gets you enough parts, even though there are dependencies between the different parts into how many pieces each xi is split. Okay, and this is it. Are there any questions?
Thank you. Yeah, we have time for questions. People have.
No more questions.
So root log K sounds like SDP, you know, ARV or something. You don't have anything.
Yes, you're right. So I hid a lot of details here. So one of the questions I didn't write the configuration LP is how you solve the configuration LP.
Okay.
The dual is essentially a generalization of sparsest cut with general demands, a weighted version where you have weights on the vertices, but the demands are not over pairs, as in sparsest cut, but are over groups. And this is why we lose the X factor. And essentially, this square root log K comes from using ALN, for embedding a matrix of negative type into L1. I didn't want to go into all these details, but I think one interesting question here is, can you shave the X factor in some way? And that I think will be very nice, because the hardness that is known for this problem is only for trees, and it is a single log. And yes, I think that is a nice challenge.
So any other questions? If not, maybe let's go to the next and final talk of the session. So the next talk will be by Rajendra Kumar on hardness of approximation of multi-LCS over small alphabet. So Rajendra, please go ahead.
So, okay, this is a joint work with Amey Bangale and Tarka Chakravarti. So let's start with the introduction to multi-LCS. So the problem is we are given k strings S1 to Sk of length at most n over alphabet sigma, and we want to compute the length of the longest sequence that appears in all strings as a subsequence. So, and we are mostly interested in the approximation of multi-LCS. And in this case, we are also given an integer L, and we want to decide whether the LCS has length greater than L or less than gamma times L. It is known that when for any alphabet set sigma, 1 by sigma approximation is easy. And this can be done very trivially by finding the longest common sequence with one character. So about the hardness of multi-LCS, there is a reduction known from max-click to multi-LCS, and this reduction almost preserves the approximation factor. There is a loss of a very small constant, and there is also a NP hardness result for max-click, which says that n to the power 1 minus epsilon approximation of max-click is NP hard. And combining these two results, we get that n to the power 1 minus epsilon approximation of multi-LCS is NP hard. But this reduction only holds when the alphabet size is at least 10. And then we ask question like, what can we say for a small alphabet size? Because in most of the applications, the alphabet size is very small, like it is almost constant. So in this work, we show that assuming the exponential time hypothesis, there is no polynomial time algorithm for gamma approximation of multi-LCS, where approximation factor is gamma is n to the power minus small of 1, and alphabet size is n to the small of 1. And the constant which we are hiding in gamma and alphabet size sigma, it differs by a very small constant. And now let's move to the details of the result. So reduction goes through two graph theory problems. One is max click and the other is densest k subgraph. And the max click and the gamma max click problem is to distinguish whether there exists a click of size k or there is no click of size at least gamma k. And the densest k subgraph problem which we use is a specific variant where the yes case is with perfect completeness. It means that in yes case there exists a click of size k, and in no case all subgraph of size k have density at most gamma. So we start with a reduction from max click to multi-LCS, which was given by Jian and Lee. And let's assume that the vertices are ordered from V1 to Vn. And then we create this, for each vertex Vi, we create string xi and xi prime. And in a string xi, the vertex Vi comes in between, and all the vertices except the vertex Vi in the increasing order of their index comes before Vi, and all the neighbors of vertex Vi which have index greater than I comes after that. And for string xi prime, Vi comes in between, and before Vi, all the neighbors of vertex Vi with index less than I comes, and after Vi, all the vertices except the vertex Vi comes. So with this construction of the strings x1 to xn and x1 prime to xn prime, if we compute the LCS, we get that there exists a click of size L if and only if there exists a common subsequence of length L. So we work on this reduction and we apply alphabet reduction. So in alphabet reduction, our aim is to first construct the strings S1 to Sn such that the LCS between any two different strings is very small. And a deterministic way to get these strings is by long distance synchronization strings. And we get the required strings. And then we replace each vertex Vi by the string Si, And note that the string SI is from a smaller alphabet size, and we create string YI and YI prime. And it's the same string, just VIs are replaced by SI. And because of just because of replacement of the string, the mapping which was previously there between the string XI and XJ, it will still be there, and we get that click of size k implies LCS of size at least k. But in the soundness, there are many issues, and some of them is like SI may not map to SI. It's also possible that SI can partially map to some SJ, and we analyze all these different conditions which we get in soundness, and by doing a more rigorous combinatorial analysis, we get that if there exists a large LCS, then there also exists a large N subgraph. And as you can see that the soundness guarantee which we get in this condition is from the densest K subgraph. So now I will state the main theorem of our paper, and it says that if there is no polynomial time algorithm for beta by 4 densest K subgraph, then there is no polynomial time algorithm for multi-LCS, where alphabet size is order of beta to the some constant. And there is, and combining over this theorem with the result of Monorangsi, which says that under exponential time hypothesis, there is no polynomial time algorithm for gamma densest K subgraph. And this result is proved for when gamma is n to the small of 1, n to the minus small of 1, and k is n to the power 1 minus small of 1. So this gives us the combining over theorem and the result of Monorangsi, we get our result. So this is it. So thanks for listening.
Okay, thank you. We have plenty of time for questions actually. So does this also give hardness for like constant hardness for constant alphabet size?
So this is not possible to get through a reduction of gamma densest K subgraph, because this problem is easy when I think K is n by some constant.
I see.
Yeah. So we can hope for something between constant and n to the small of 1. But that is still not known because of there's nothing known for gamma densest K subgraph.
I see.
So I have a question. Do you know what happens for gamma smaller, like logarithmic in n?
For densest K subgraph. So are you asking for densest K subgraph or LCS?
LCS.
LCS, nothing is known. Like I'm saying, this is the first result which is for sublinear size alphabet.
Mm-hmm.
It's open. Right now, nothing is known.
Thanks.
Any other questions? So I don't see anything in the chat either. So, okay, so thank you for all the speakers in this session and Rajendra. And we'll meet in 20 minutes again for the next session at 5 o'clock here and 8 PST. Thank you.